So the method that we are using so far is the following. For each edge u comma v that we find in the list of edges, and we are pretending here that these edges are coming in dynamically, we check what the component IDs of u and v are. If they are not the same, we apply the union operation to unify those two components together, and we reduce the number of connected components by 1. And if we had to print out or output the number of connected components after seeing each edge, we could do that here. We could just say print components, and that would print out the latest value of the number of connected components. So we'll assume that before we have seen any edge, this value starts out being n, and after seeing each individual edge, it keeps getting updated. So if it turns out that u and v lie in the same component, then we won't implement the union operation. We'll just directly come here and print the same value as before. Otherwise, we'll take the union, decrement it by 1, decrement the number of components by 1, and print out that decremented value. Now in the last video we saw that what we called as the quick find approach to finding and taking the union took quadratic time. So an individual find operation took constant time. It was a trivial operation, but taking the union was more expensive, because we had to basically, in the worst case, change the ID, the component ID of everyone in the connected component on the other side. And so in the worst case, we saw that the total amount of work done across this whole process would be order n square. Let's now try to see if we can improve the cost of the union operation to something better than order n for each union. So suppose we have an edge between u and v that has just arrived. So just before the arrival of this edge, let's assume that u was in its own component. That means the component ID of u was u itself, and let's say v had 6 vertices in its component, which are all shown in green here. So what we were doing was we were visualizing v changing its component ID or its religion to the same religion as u, and that conversion also triggers a conversion of all the other members in the connected component to which v belongs. But we also know that was an expensive operation, so we don't want to do that. In fact, let me revert back to the moment before v got converted. So let's imagine for a second that v is the king of his group, and so everyone else in the connected component is in effect following v. Maybe v has a minister, and the minister has some family member, maybe his son, who's also following him, and so in the same way, maybe the king also has a treasurer, and the family of the treasurer is basically following him. So in this kind of imaginary society, what would happen if the king changed his religion is that the other members of the society would by default follow the religion of the new religion of the king. They don't have to be explicitly colored blue. Their component ID does not have to be explicitly changed to the component ID of u. We record the fact that they are just following this particular king, and so whatever the religion of that king is, that is going to be treated as the religion of all the followers of the king. And so when two components need to be unified, instead of changing the component ID of everyone in this particular connected component, what we will do is we will only change the component ID of the king of that component, the leader of that component, and assume that everyone else's component ID has changed by that. Now we haven't explicitly changed the component ID of say this vertex, but if we were asked what is the component ID, what is the religion that you are following, well, this vertex would say, well, I'm just following the religion of my father. And what if we go to the father of that vertex and ask what is the religion that you are following, this vertex would point me to the king. He would say, I'm just following whatever the religion the king is following. Now what religion is the king following? Well, the king would say, well, I'm following the religion of you, whatever that is. And then when we go and ask vertex u, what is your religion, uh, vertex u would say, well, I am the prophet of this religion, I'm only following myself. So that's the answer, that's the final answer. What is the religion that this particular vertex was following? Well, it's basically the component ID u. Now it's not that the component ID u is going to be stored explicitly with this vertex. Let's say this vertex is x. This doesn't mean that at index x in the component ID we're going to find a u. No, at index x we're actually going to find the value y, where y is the index of this vertex's father. So we just look up that index and we then go and check well, what religion is vertex y following, and vertex y says that, well, I'm following my king. So the ID of the king, which in fact here is v not k, that would be found in the component ID array for y. And so then when we go and look up the index v, we are now going to find u written on it. And so we then go and look up vertex u to see what the component ID of that is, and we find u itself there, and we thus know that we have reached the prophet of that religion, or the leader of that religion. There is no other person that this vertex is following, and so this is actually the component ID of x. Now why are we doing this? We are doing this because when we get a new edge from u to v, all we need to do is to change the component ID of v to match the component ID of u. We don't have to change the component IDs of all the followers of v. So this enables us to effectively do union in constant time if we knew that this vertex v was actually the leader of that religion. And what if v was not the leader of that religion? So let's say that we had a vertex, let's assume that we have a new edge now coming in between w and x. Okay, w and this lowly person x, who decides that he wants to change his religion. So let's say that w is a charismatic figure, and he convinces x to change his religion. Now we are not going to just change the component ID of x to point to w, because if we do that, we would still have to do the work required to change the IDs of all the other members in the component of x to this new religion of w. And in fact u itself is part of the component now, since we are assuming that the edge from u to v has already come. So when this new edge between w and x comes in after the edge between u and v came, we now have to change the affiliation of everyone in this component to point to basically be the component ID of w. How do we do that? Well, we don't want to change the component ID of x to be w. Rather, we really want to go up this chain to ultimately reach the prophet of that religion, right? And the prophet is this vertex u, and we're going to pretend that it's that prophet who's going to change his religion, subordinating himself to the religion of w. And so when that happens, we don't have to worry about changing the religious identity of all these other followers, right? They'll just follow blindly whatever U follows. So we just have to walk up the path from X to the prophet of that religion and change the identity of the religion of that prophet. So that means once we know who the prophet is of that connected component, who the leader is, we just have to change the component ID of that leader to be equal to the component ID of the vertex on the other side. Now you may ask, well, what do we do in the most general case? So suppose we have two existing connected components here, and let's say the leaders of these two components are U and V respectively. What if the next edge we see is between X and Y? So X is an sort of an intermediate node here, and we are saying that this X needs to be unified with this Y, right? This edge between X and Y is unifying them, which means the two components have to be merged together. So we will again not try to do this at the level of X and Y. Rather, we will pretend X as going to, you know, the leader of that component and telling the leader that, you know what, we need to have our entire component unified with the component that Y belongs to, and Y is going to do the same thing. Y is going to go up to the leader of its component, which is V, and tell the leader that you know, we need to unify ourselves with whoever the leader of X is. So if we know who the leaders of X and Y are, they are U and V. So instead of trying to unify the components of X and Y, we will actually unify the components of the leaders of X and Y, right? So we'll treat the edge between X and Y as actually conceptually an edge between the leader of X and the leader of Y. So that means when we are given an edge between X and Y, we first have to do this job of finding out who the leader of X is and finding out who the leader of Y is, and then change the identity, the component identity of one of those leaders to be the identity of the other leader's component. So again, we are assuming so far that we are breaking, you know, we are making that decision as to which leader changes its identity arbitrarily. So let's say that V is again going to change its identity, not U. So we will basically have the component ID of V change to the component ID of U. So the union operation at the end will effectively do the unification in this way. The leader of the second component is going to change its identity to the component ID of the leader of the first component. And so we will take a constant amount of time to do the union once we know the leaders of both components. But of course we have to do more work now to find out who the leaders are. So starting from X, we have to walk up this path up to a point where we find that this vertex follows no other vertex but itself. Likewise, we have to start from Y and walk up this path, you know, find out who Y is following, find out who that vertex is following, up to we reach a, you know, until the point where we reach a vertex that is following itself. And at that point we know that we have the leader of that component identified, and we then do this constant time operation of taking the union, which is basically converting the leader to the component ID of the other leader. So let's see how to modify our pseudocode to handle this way of doing union and find. So whenever we see a new edge between U and V, what we will first do is find the leader of U and find the leader of V. Now it's possible that both U and V already belong to the same component, in which case LU is going to be the same as LV and we have nothing more to do. But in general, it is possible that the two leaders are not the same. If they are not the same, that means u and v belong to different connected components which now need to be unified. And how are we going to unify them? Well, we will just take the component ID of the component ID of LV and reset it to the component ID of LU, and this effectively does the unification between the two components. And once we have that unification, we can again decrement the number of connected components by 1, and once we are outside this if loop, if condition, we can print number of connected components. So if LU and LV were the same, we wouldn't have done the unification, we wouldn't have decremented the number of components, we would still print the same value as before. So again, we are assuming that the number of components starts out being n before we have seen any edge, and this is how the whole process goes. Now we do need to write the code to find who the leader of each component is. So let me do that here. Let me just write a function that will find the leader of an arbitrary vertex, say x. Well, if we find that the component ID, if we find that the component ID of x is already x, right, x is following itself, then clearly the leader of that connected component is x itself. Otherwise, we have to walk up that chain. We have to walk up the chain from x until we reach a leader. So in that case, let's start out with a current vertex pointing at x, and then we'll say while the if we look up the component ID of the current vertex and we find a different vertex from the current vertex, right, that means this current vertex is following some other vertex, we have to walk up to that other vertex. So we have to reset current to be the component ID of the current vertex. So this is equivalent to starting from x and taking a step up to go to the parent of x, and we keep doing that. We go on walking up to the parent as long as we see that the current vertex we are at is following a different vertex. And when we come to this point where we exit the while loop, we have reached a vertex who is following itself, and so at that point we can return the identity of that vertex to be the leader of the component to which x belongs. In fact, you can notice that this code is actually redundant. I can eliminate this because that is if x is already the leader of x, we will handle that, since we will not even enter the body of the while loop. We will directly see that component ID of current is equal to current, and so we will directly return the current vertex, which is initialized to x itself. Now with these changes, you might notice that the find operation is no longer trivial. We have to start from the given vertex and keep walking up until we reach the leader of that vertice's component. So it's no longer a constant time operation, but once we have the leaders on both sides, then the unification, the actual unification, is a one-line operation. And because that actual union can be done in constant time, we're going to call this method as quick union. So let's try to analyze the worst case complexity of this quick union method. We know that the number of union operations is going to be at the max n-1. We know that from before. The number of find operations will be in general 2 times m, since we have to find the leaders of u and v for every edge u comma v that comes in. So 2 find operations per edge, 2m in total. Now what's the complexity per operation? The complexity of an actual unification operation is constant time, because once we have found out who the leaders of u and v are, we just have to change the component ID of one of the leaders to be equal to the component ID of the other leader. So the real cost actually lies in the find operation this time, because it's no longer a constant time operation. The question is, how worse can it get? How long can the path be from x to the leader of x if we follow a chain of these union find operations? How bad can this get? Well, you can imagine an adversary constructing an input which can force your algorithm to actually have find run in order n time. How would that happen? Well, suppose we have a component like this. The next edge that I send to you may be between an isolated vertex w and x. Now the addition of this edge is going to force you to find the leader of x by walking up this path to the leader of x. Let's say it's lx, and based on the way you are choosing how to how to pick the leader who converts, we are assuming by default right now that the leader who converts is going to be the vertex which is the second vertex in the pair. So lx is going to convert to the component ID of or the religion of w, and that means lx is going to follow w, and that is going to make w the leader of the whole component. So lx now becomes a follower of w, and this whole chain is preserved as before, with x being at the bottommost level. And this could keep on happening. Maybe the next edge that comes in is between a vertex called y and x. Okay, so we have to search for the leader of y and the leader of x. Leader of y is y itself. The leader of x is this time w, and so we decide to change the component ID of w to point to y, and this means our chain grows further. So y has w as its child, w has lx as its child, and so on. So this process could have looked like this right from the beginning. Right from the beginning, when all the vertices were isolates, we could have started forming components in a way that at the end everything is chained up inside a single component, and then you have an isolated vertex as the second component, and this chain just keeps getting longer and longer. So every time we do a find on this larger component, that's going to take an order n time. Now strictly speaking, it's not going to take order n time from the beginning, because in the beginning there's only every vertex is isolated. But as this chain grows longer and longer and longer, you can see that every time we do find on x, initially it might have taken constant time, then it might have taken 2 steps, then it might take 3 steps, and by the time this chain grows to size n-1, this might take n-1 steps. And so the total cumulative cost of doing find x repeatedly, n-1 times, would be quadratic, would be order n square, right? And so in the worst case, we are again going to end up with quadratic time complexity. You can see here that the union operations by themselves take only cumulative of linear time, but these find operations can get expensive. Even if we assume that the graph is sparse, we have the number of edges is proportional to the number of vertices, we are still going to end up here with a quadratic complexity for find, and that is going to dominate the complexity of this entire process, which is still going to remain at order n square. So it looks like doing this quick union didn't help, because even though we managed to improve the speed of the union operation, the speed of find degenerated to order n. And likewise in the quick find method, even though we could do the find operation instantly, we saw that in the worst case the union operation would take order n time.
Want to become a software engineer at Google? You can, like thousands of our students. You just need to learn from those who've already cleared FANG interviews. At Interview Kickstart, our interview prep courses are developed and taught live by 150 plus instructors from Tier 1 companies like Google and Facebook. Our courses are tailored to help you crack software engineering domain interviews, including back-end, full stack, machine learning, embedded systems, data science, and more. To learn more, book your free webinar slot today